All right, we're going to work through the final review. Question 1, we have two rails connected by a resistor and a bar that can slide along the rails. The metal bar is 10 centimeters long, has a mass of 50 grams, and it falls at a constant speed of 1.5 meters per second. So as it falls, what happens? Well, there's several ways that we can look at this. We can look at this as a bar moving in a magnetic field, which we have the equation delta V equals BLV. Where capital V is voltage and little v is velocity. We can also look at it as a loop with a changing flux. So if we look at it as a loop with a changing flux, EMF we know is N delta flux over delta T, where N is the number of loops, in this case, just one loop. Either one of these approaches work. Let's see what we're actually looking for here. We're asked for the magnetic force on the bar, but we're told that it's falling, so under the force of gravity, and it's moving at a constant speed. So if we're falling under the force of gravity, and we're not accelerating, then the magnetic force has to be equal to the force of gravity, because if V is constant, A is 0. So our sum of forces is 0. Magnetic force minus the gravitational force equals 0. Magnetic force is equal to mg. All right. Unit conversion, 50 grams is 0.05 kilograms. Multiply that out. 0.4905 newtons. All right, there's our magnetic force. That was part A. Part B says, find the power dissipated by the resistor. Okay, if we want to find the power, we know that power is energy per time. Where's the energy coming from in this case? Well, constant velocity means constant kinetic energy. So there's no change in kinetic energy, but we do have a change in potential energy. So that change in potential energy is going to be dissipated by the resistor. So our potential energy in this case is coming from gravity. Gravitational potential energy is mgh. So if we want to find the power, we're going to look at the change in energy, mg delta h, over change in time. Well, if we look at delta h over delta t, our velocity is pointed downward, so that's our velocity. So mgv will be our power. 0.05 kilograms times 9.81 newtons per kilogram times the velocity of 1.5 meters per second. So our power is going to be 0.736 watts. And that's watts because our kilograms cancel. We're left with newtons meters, which is joules per second, and joules per second is watts. Part C says find the current induced. Well, since we have the power now, and we know that power is going to be dissipated by the resistor, we can use our electrical power to find the current. So power is current times voltage. We don't know the voltage, but we do know the resistance, and we know that V is IR. So let's substitute that in for our voltage. Power is I squared R. So I then will be the square root of power divided by resistance. Zero 0.736 watts over 1 ohm and the square root. Zero 0.858 amps. All right, so now we have the current. Part D asks us to find the magnetic field strength. All right, how do we want to find the magnetic field strength? Well, we know the magnetic force, and we know the current. We're looking for the magnetic field strength. What equations relate this? Well, if we look at our formula sheet, the force on a wire is BIL sine theta. Well, do we know L? Yeah, we know the length of the bar as well. So the only thing we don't know is B in that equation. We can use that equation. Our magnetic force on a wire is B times the current times the length of the wire times the sine of the angle between the field and the normal to the direction of the current. The direction of the current in this case is in the plane of the page, so the field's perpendicular. So sine theta is 1. We're solving for B, so B will be the force divided by the current times the length of the wire. The force we found in part A, 0.4905 newtons. The current we found in part C, 0.858 amps. And the length of the wire is 10 centimeters or 0.1 meters. So our magnetic field strength is 5.72 Tesla. Pretty large. Number two. Number two says find the velocity of an electron moving in a circle of radius 10 centimeters. So we have an electron moving in a circle with a radius 10 centimeters or 0.1 meter. And it's perpendicular to a magnetic field of 2 Tesla. Okay, I've drawn my electron moving in a clockwise circle. So is our field either into or out of the page? If we assume that our field is out of the page, then the force on my electron would be away from the center rather than into, right? Because if I do my right hand rule, my thumb points towards the center, but an electron's negative. So the force on an electron would be away from the center. So my magnetic field is going to have to be into the page so that the force on my electron will be towards the center. So my magnetic field is into the page for this drawing. And you could draw it either way. It's just changing your point of view. If I'm standing behind it, it would look like the field is pointed the other direction and the circle would appear to be counterclockwise. All right, so we know from physics 131 that in order for something to move in a circle, that means it's always accelerating. So we know that the sum of forces is not zero in this case. Let's look at our free body diagram. So what forces are acting on our electron? Well, the only force acting on our electron is the magnetic force. And it points towards the center of the circle. Well, we know that if we have unbalanced forces, then F is equal to ma. And if we're moving in a circle, we know that A is going to be the centripetal acceleration. So my only force is the magnetic force, and it's going to be equal to m times the centripetal acceleration. My equation for the magnetic force on a charged particle is qvb sine theta. Again, sine theta is 1 here. We're perpendicular to the field. And our equation for centripetal acceleration is v squared over r. All right, what do we know? What are we looking for? We're looking for v. We know q because it's one elementary charge. It's an electron. We're given b. We're given the radius. And we know the mass of an electron. So this is everything we need to be able to solve. So first, let's divide by v. We'll have qb equals mv over r. Multiply by r, divide by m. And we're left with qbr over m equal to v. So what is our velocity in the end? Q is 1.6 times 10 to the minus 19th coulombs. B, we were given 2 Tesla. R is, I think it was 10 centimeters. Yep, 10 centimeters, so 0.1 meters. Oops, R is in the denominator. Oh, no, it is in the numerator when I bring it over. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Number crunching. Get 3.51 times 10 to the 10th meters per second. All right, is that realistic? No, that's greater than the speed of light. So this is not real. If I gave you something like this on a test with an unreal velocity, performing all the work correctly would get you full credit, but I would probably give you a bonus if you noted that, yeah, this isn't real. And normally I don't give you things that are not real unless I'm looking for something like that. So if you asked me during the test, I would let you know, like, yeah, that's correct. I'm just looking for you to notice that. Because one of our checks normally is, does this answer make sense? And doing all the work properly, this answer doesn't make sense. So this electron cannot move in a circle of radius 10 centimeters in this magnetic field. It just doesn't happen. All right. Number 3. Number 3 says 2 coils are wound on a common core. So, and it gives us the radius of the core. So it's going to be a cylindrical core. So let's assume from one end, we have our primary coils. On the other end, we'll have our secondary coils. And they share the same core, so they're going to share the same magnetic field. I'm just going to assume a direction for B here. It'll depend on the direction of the current, but I'm just going to assume. It doesn't matter since we're only looking for the magnitude here. We're told that the radius is 2 centimeters. And the field is 5 times 10 to the minus 3 Tesla. The second coil has 100 turns. And the resistance in the second coil is 1 ohm. What is the current induced in the second coil when the first coil's turned off and takes 350 milliseconds for the field to dissipate? So the field dissipating means that B final is 0. B initial was our 5 times 10 to the minus 3 Teslas, but our B final is going to be 0. And our delta T, I'm going to go ahead and put it in seconds, 0.35 seconds, just unit conversion from millisecond to second. We're talking about induction here, so we're going to look at EMF in delta phi, the flux over delta T. So the change in flux over change in time times the number of coils. And this will give us our voltage. Were we asked for voltage or current, though? We're asked for the current induced in the second coil, but we were given the resistance. So we're going to find the voltage to figure out what the current is after we use the resistance. All right, we need the fact that flux is area times B times cosine theta. We're going to assume that they're aligned here. The way I have it drawn, N is along, my B is along the axis of my core, which would be the normal vector for the coils wrapped around the core. So my cosine theta here would be 1. So just area times the flux. The area in this case is just pi r squared. So we've got 100 turns times flux final, which is 0, minus flux initial. Oh, do I not even have to calculate this? Because we were given, oh, we're given B. We're not given the flux. Okay. We're given B is 5 times 10 to the minus 3 Tesla. And our area will be pi r squared. So pi times 0.02 meters squared. So that's our initial flux and our final flux divided by delta T, 0.35 seconds. Let me move this over a little bit. It's in the way. All right. And we're ready to plug in and find our EMF. So our EMF is going to be 100 turns times 5 10 to the minus 3 Tesla times pi times 0.02 meters squared divided by 0.35 seconds. All right, now I'm getting millivolts here. 1.795 to approximately 1.80 times 10 to the minus 3 volts. All right, V equals IR. So I will be V over R. Our resistance in this case is just 1 ohm. So the current's going to be 1.8 times 10 to the minus 3 amps. Since we have 1 ohm resistance. Just milliamps, right? Nothing really strong here. And I don't think that's too surprising given that our magnetic field is so small, right? 5 times 10 to the minus 3 Teslas here. I'm just going to crunch the numbers again, make sure I didn't make a mistake, just because that is that small. The area is kind of small too. Yep, that's the correct answer. All right, number 4 says a light source is 40 centimeters from a converging lens with focal length 15 centimeters. Describe the location, magnification, and sketch the ray trace diagram. Number 4, 15 centimeter focal length, 40 centimeter location, so a little more than twice. Remember, when we're talking about lenses, not about spherical mirrors, we get a focus on each side. And for lenses or mirrors, we have 3 rays of interest. We have parallel, center, and focus. So if we go in parallel, we come out through the focus. If we go in through the center, we go straight. If we go in through the focus, we come out parallel. Change colors here. In parallel. Out through the focus. In through the center, keep going straight. In through the focus. Out parallel. My sketch is a little rough, so they didn't line up well, but they should all intersect. And then that's where our image occurs, right? It does say sketch, not construct a diagram. So if they don't line up perfectly, that's fine, but you should be able to tell what's going on. All right, so from this, we can tell that our image is going to be inverted. And it's going to be real. I can't really tell if it's enlarged or not from this diagram because it is a rough sketch. So I don't know what the magnification looks like. But we can find the location and the size of the image using our equations. So we know 1 over P plus 1 over Q is equal to 1 over F, where this is the object distance, this is the image distance, and this is the focus. So we were given our object distance of 40 centimeters and our focal length of 15 centimeters. You don't have to convert to meters here because everything's in centimeters. It's all going to cancel out in the end and leave you in centimeters. Whichever unit you stick with, you can carry through. So we'll have 1 over Q is equal to 1 over 15 centimeters minus 1 over 40 centimeters. And then take the reciprocal. Q will be 1 over 15 minus 1 over 40 reciprocal centimeters, right? We had centimeters on bottom. When I take the reciprocal, it'll be on top. So 1 divided by 15 minus 1 divided by 40. And then equals and x to the negative 1. All right, I get 24 centimeters as my cube. Right, the last, so we have our location. And we can look at our magnification factor, which is minus q over p, if we want to describe the height of the object or the image. Minus 24 centimeters over 40 centimeters. That be 6/10, so 0.6 negative. So our magnification factor is 0.6 and it's inverted, right? We knew from our sketch that it was inverted. We just didn't know if it was bigger or smaller because of how rough my sketch is. And here we can see that it is smaller. My center line's kind of curvy though, and I think that's what threw us off there. All right, so we've got the location and the magnification. And we said it's inverted and real. Recall that for a lens, real images will be past the lens, whereas on a mirror, they'll be on the same side because there is no past a mirror, right? That's a virtual space. All right, part 5 has two lenses. We have a diverging lens, focal length 10, that receives light from a source 30 centimeters away. Let's go ahead and start sketching this before it gets too complicated. So we have our diverging lens and we have a source 30 centimeters away. A converging lens of focal length 5 is 12 centimeters past the diverging lens. So here's a converging lens that's 12 centimeters away. And our diverging lens focal length is 10 and the converging is 5. So I'm going to write it as minus 10 for the diverging lens. Notice they were shown as absolute values, and we know for a diverging lens it has a virtual focus, so it's a negative focal. All right. Describe the image, size, orientation, location, real, virtual. So everything that we just did for number 4, but now we're looking at a 2-lens system, and we have a little more complicated because we have a diverging lens as well. So I'm going to start just like we did before. I come in parallel. For a diverging lens, though, I treat it as if I came from the focus. So it's going to go out this way, and my diagram's not really big enough to do this. This would be the line for this lens and the foci for the second lens. Well, they're going to overlap, aren't they? Because they're only 12 centimeters apart. I should have color-coded my lenses. Let's fix that. All right, if this is 12 centimeters, 10 centimeters is about there. So this really should have been to scale too. Yeah. All right, that looks pretty good to scale. 5 to scale out of that would be about here. So this would be F2 and this would be F1 because they're 12 centimeters apart. All right. This distance for F1, my other F1 would be about here. And if this is 30 centimeters and that's 10, then 3 times as far, right? So my object is going to be back here. If I wrote the T instead of right, arrow like we normally do. All right, so if my object's 30 centimeters away, this is a little closer to scale, maybe this will work better. Let's increase the size of our converging lens as well. All right, now let's try sketching. In parallel, from the focus. That's not really a good line for our second lens, is it? We don't really know where that goes. So I guess it doesn't make a lot of sense to draw a sketch for the two, one this way. What was my green? Straight through the center. Straight through the center here to here. And then I use light blue for the other. In through the focus. But that means the focus on the far side, right? So heading toward this focus will come out parallel. And we trace that back to form a virtual image back here. All right, and then that is going to be the object for our second lens. So let's just do these calculations. If we look at the first situation, so P1 was 30 centimeters, and F1 is minus 10 centimeters. Then 1 over P plus 1 over Q equal to, not plus, 1 over F. We get a value of Q that's inverse of 1 over F minus 1 over P. So 1 over negative 10 minus 1 over 30, and then take the inverse, and that's in centimeters. So 1/10 minus 1/30, oh, negative 1/10, so minus 1/30. And then take the inverse. 7.5 negative. All right, so that agrees with our sketch, right? We have a negative image distance for the first one. So now, if this distance is 7.5 centimeters behind the first lens, and the second lens is 12 centimeters from the first lens, then the total distance from my object for the second lens, which is the image of the first one, is 19.5 centimeters. So now if we look at P2 equal to 19.5 centimeters, and focal length 2 equal to 5 centimeters. We can then say 1 over P2 plus 1 over Q2 is equal to 1 over F2. Same equation here. So Q2 is going to be 1 over F2 minus 1 over P2, and the inverse. Well, I hadn't plugged in units again. So 1 over 5 minus 1 over 19.5, and then take the inverse. Inverse 6.72 centimeters. All right. Since these lines aren't our lines coming in parallel, it's kind of hard to sketch a two lens problem. What we can do is, I need more colors. I'll use a pink instead of a red here. Look at where the image is and treat it as if that's your object for the first one. So we'll have it coming in parallel, and I only drew one focus, and out through the focus. For my blue, let's use a darker blue. Through the center straight. And for the green, we'll use a darker green. This one should be in through the focus, out parallel. In through the focus, out parallel. Gives us an image here. Maybe that gets a little busy there, but maybe you can zoom in on it and it'll be visible. There's too many overlapping lines there. All right, but our calculation shows it. So we got a positive Q, so it's a real image. And from our drawing, we can tell it's inverted, but how do we figure that out if we're just doing the math, right? Well, we know that the magnification factor is minus Q over P. And we can find that for lens 1 and for lens 2. So let's find our magnification factor for lens 1. It's going to be negative 7.5 centimeters over 30 centimeters. So 7.5 divided by 30 is 0.25. All right, our magnification factor for lens 2 minus Q2 over P2. Let's see. What was P2 was our 19.5. And Q2 ended up being 6.72. All right, so our magnification factor there is minus 0.345. All right, and our total magnification factor is just going to be the product of M1 and M2. If we multiply those together, we get negative 0.086. So it's much smaller than the original object. And it is inverted. Our final magnification factor came out negative. So we did get an inverted image as predicted. Let's see, did we answer everything asked? We said size, orientation, location, real and virtual. We said it is a real image. It is inverted because we got a negative magnification factor. And it's located 6.72 centimeters past the second lens. And it'll be that magnification factor where we said size. Were we given a height for it? No, we weren't given a height. So the magnification factor would describe the size of the image.